Good morning. Welcome to this second session of our annual symposium. I'm Cheryl Prager, Professor of Mathematics at the University of Western Australia. I will be the chair of this session celebrating the physical and earth sciences in Australia, with presentations by two extremely distinguished scientists. As a mathematician chairing this session, I want to say how proud I am of the great advances in the mathematical sciences over the last 60 years, many of them achieved by Australian mathematicians. And it's not only advances within the mathematics discipline that delight me. I completely agree with Australia's chief scientist, Professor Ian Chubb, who said recently, and I quote, "Most of the great innovations that have changed the way people live over the past 2 centuries were enabled by mathematics." Thus, not only is mathematics important and flourishing discipline in its own right, but also mathematics underpins much of the work that has been and will be reported by the symposium speakers today. Our first speaker in this session, whom I have the absolute pleasure of introducing, is Professor Brian Schmidt, Nobel Prize winner in physics and Laureate Fellow in astronomy at the Australian National University. In 1994, Brian Schmidt and colleagues formed the High Z supernova search team to measure the expected deceleration of the universe using distances to type 1a supernovae. Schmidt led the team from Australia, and in 1998 the first evidence was presented that the universe's expansion rate is accelerating. This contradicted the prevailing theory of the time, and the rest, as they say, is history. The discovery of the accelerating universe was named Breakthrough of the Year by Science magazine in 1998, and Brian Schmidt was jointly awarded the 2011 Nobel Prize in Physics, along with Adam Rees and Saul Perlmutter for their groundbreaking work. Brian is also an enthusiastic winemaker, particularly of Pinot Noirs, and runs the Mypenrite vineyard not far from Canberra. Professor Brian Schmidt, Companion of the Order of Australia, Nobel Laureate, Fellow of the Australian Academy of Science, Fellow of the Royal Academy, welcome. I invite you to address us on the history of physics and astronomy in Australia.
Thank you, everyone. It's a great honor to be here and an incredible challenge that I have been given to go across the incredibly diverse range of physics that we have here in Australia. So I've called my talk Physics Since Federation, and I really need to go back to Federation because physics pre-World War II had a couple interesting things that happened, fundamental things that happened on the world stage. So pre-World War II, physics was taught in the sandstone universities as an undergraduate course. We were isolated here in Australia by the great distances to the US and Europe, where most of the action was going on. We did not have PhD programs, and we produced a very good set of undergraduate students the best of whom traveled overseas for further study. And there are many great physicists in that era were created that way, who ultimately usually went off to the UK for further study. And the great distances of the ship meant it was many months to get around and very expensive. And so the ability to have a vibrant program here in Australia was just simply limited by the difficulties of communication and collaboration. So if we look in detail at our first Nobel Prize, done by William H. Bragg and William L. Bragg, it's really quite remarkable when we think about it, given the state we had. And this came really quite soon after Federation. So William Bragg was from Cambridge, graduated first-class honors in mathematics in 1885, and was immediately appointed to the University of Adelaide, where he came here and started studying. He met Rutherford, which turned out to be a lifelong relationship that he had with Rutherford. And Rutherford got him excited about working in radioactivity and X-rays, something that he turned out to excel in. He was able to build up his own, essentially, instrumentation group, where he did a lot of the work himself. And this saw him become a world expert in Adelaide, and immediately landed him a job in England, where he then left in 1908 to go take up a position in Leeds. His son was born in Adelaide in 1890. His father did the first Australian X-ray in 1895, one of the first X-rays in the world, when his son broke his arm, and he went in and looked at his son's broken arm, probably something that did not lengthen his life, given the dose he would have gotten. Bragg was a very good student. He graduated at the age of 18 from the University of Adelaide, went off to Trinity College in Cambridge, got a first-class honors degree there, and then worked on what is the moral equivalent today of a PhD. Well, working on this PhD at Cambridge, he was working with his father, who was up in Leeds, who had developed what we would consider to be an X-ray spectrograph, and was able to go through and formulate the thing that won he and his father their Nobel Prize. And Bragg, still to this day, at the age of 25, is the youngest winner of a Nobel Prize ever. And Bragg's big discovery was that when you looked at things and you bounced X-rays off them, you saw a pattern. And they understood that pattern as being the X-rays essentially scattering off atoms, individual atoms, inside, for example, a crystalline structure of graphite or a diamond, and that by that spacing of that crystalline structure, you could get interference patterns where the light essentially lined up, the waves of the light lined up for constructive or deconstructive interference. And that gave you a pattern, a regular pattern, from which you could understand using Bragg's law, where you looked at essentially the angle of the incident X-rays onto the structure, and then the pattern that emerged was related to essentially how those atoms were arranged. This is one of the most useful discoveries of all time. It's one of the really big Nobel Prizes of physics. It was used almost immediately to realize how diamonds were structured, how graphite was structured. And if we look at how it's being used today here in Australia and other places, for example, here is the X-ray scattering picture that helped discover DNA. That work was done in the lab of Bragg, Jr., who oversaw Watson and Crick and others at this famous photo where they were able to disentangle the helical structure of DNA from that pattern. Been used more recently, for example, to go through and look at the structures that allow influenza and other viruses to create antivirals in the form of Relenza here. In this diagram, that's again an X-ray scattering experiment, and it can be used to do things like iron ore characterization. Almost every discipline in science uses Bragg scattering in one way or another. It's a very fundamental underpinning part of science today, and it will continue to be so because it is so incredibly useful. The rise of physics in Australia, I think we can trace really to our first Academy president in Mark Oliphant. Now, Mark Oliphant graduated from physics, University of Adelaide in 1922, and then went off to study nuclear physics at Cavendish Lab. It took a few years to get there. He had to actually pay for his way. And he was the person who discovered tritium, that's a hydrogen atom with 2 extra neutrons. Helium-3, that's a helium atom missing a neutron compared to the normal. And he was able to demonstrate the fusion of tritium and deuterium for the first time. He realized the power of fusion and eventually fission. He went up and started working at Birmingham, where he then worked in something completely different, where he developed short-wave radar and what we call the resonant cavity magnetron. Most of us have more or less one of these in the form of our microwave oven now. And he was able to make small, compact radar units, which were developed during World War II, out of his group. He, if you read the very good Making of the Atomic Bomb, I would argue probably the best science book ever written, his role in getting the Manhattan Project started is seminal. He is listed by many people as the most single important person in starting Manhattan Project. And it wasn't done for the desire to make the bomb. It was done out of the fear that the Germans would make the bomb. He had the realization, more than any person, that it was possible to make successfully a nuclear bomb. And he spent his time convincing the US government, who had the resources to undertake this development in the United States, to get started, and convinced the likes of Lawrence, of Fermi, and then ultimately the US government that this is something they needed to worry about, and he was successful. He worked on that project for a couple years, 1943 onwards, and at the end of it, he noted that it was, to him, very impressive that they were actually able to make the bomb in the time they did, but was appalled that it was actually used on humans, and became quite a strong advocate for non-proliferation in his later years. He came to Australia in the late 40s to help start the Australian National University, and he is certainly one of the people who we can look at for the reason why the ANU exists, probably more than any single person. When he came to the ANU, he initiated the construction of what was going to be called the cyclosynchrotron, a huge, hugely powerful accelerator similar to what we have in the synchrotron today. And it was way out there at the time, and it was done, I would say, through a fairly ingenious, but as ultimately high-risk way of doing things. What started out as a grand vision in about 1950 grew to be a bit of a monstrosity in a time when the US, the UK, Europe, and the Soviet Union were all dumping huge amounts of money, more money than he was able to get into the project here in Australia. And so this project did not go as well as it might, and you can see the remnants of what is the homopolar generator, which is where that synchrotron eventually ended up, or that accelerator eventually ended up creating this huge disk that you could spin up and generate, when you released it as almost a giant capacitor, huge amounts of current. And that was to drive the accelerator, but ended up being useful to do all sorts of other interesting experiments, but certainly not what was originally intended. It was referred to by many physicists across Australia at the time as the white elephant, probably aptly named, and I think Mr. Messel last night was probably one of those people who said that. So I would not say it was the most successful effort here in Australia, but he did set up what is still the largest physics group in Australia, and started essentially a modern generation of physicists and the way physics is done in Australia to this day. But as the most lasting legacy is going through and spending a lot of his time setting up the academy of which we sit here in the Shine Dome today, and that is almost certainly his greatest Australian legacy, although you see his scientific legacy, especially from his work done over in the UK and the US, is considerable. Also after World War II, we had some interesting technology, again related to radar, which developed into radio astronomy. So we had a bunch of people who had gone through and figured out how to make radar easily deployable into the Pacific, and that was done by engineers here in Australia, and here are three of them who later became radio astronomers. And I want to make particular note of Ruby Payne Scott, whose story is both inspirational and tragic. So she was very mathematically inclined, physicist trained at the University of Sydney, who then worked on these radar systems. And she noted that it would be possible to go through and look at some of the sources that were known to exist in the sky. Their notion of where they were in the sky was very, very poor, because radio waves have very long wavelengths, and when you go through and make a telescope, especially in the early days, you sort of knew that the source was up there somewhere in the sky and not much else. So it was very difficult to tell, other than the sun, what was going on. And so she devised an ingenious idea, which will look very, very similar, if you think about it, to what Bragg did. So you're essentially Bragg scattering, but in this case with radio waves. And the idea would be, as the radio waves came in from whatever source, they would bounce off the ocean up to their radar detector, and the other ones would come straight in. And if you got the distances right, you could get constructive or deconstructive interference. And that essentially allowed the telescope to not just be this little dish radar antenna that was limited by the diffraction limit of where it could see things were coming from the sky, but rather a telescope equivalent in size from the distance where the light reflected off the ocean to the radar, greatly enhancing their ability to identify sources, and it allowed them indeed to identify some of the first sources in the sky. This work is the basis of what we call interferometry, and she wrote the first mathematical equations, but as was the time of those days, she was married to someone, and that turned out not to be allowed if you were a woman to work at the CSIR, as it was known at the time. And when she became, and she was able to hide that, and when she became pregnant with Academy member Peter Hall, the game was over, and she was forced to resign, and to the loss of Australian science, it is amazing to me that we could throw away someone like her in this country back then. I'm sorry it bothers me. All right, I will recover myself. I wasn't expecting to do that, but it does incredibly bother me. From that work, we had an explosion. An explosion is a collective noun for radio telescopes through the period of 1954 through 1963. A lot of these things were down out at the Fleurs site, and these were largely operated by CSIRO, as it was becoming known as. And Fleurs is now known to you as Badgerys Creek, so likely to be the site of a future, or maybe not, airport. So the first of these, Mills Cross, shown here in the top picture, a huge expansive cross of radio telescopes, which could then go through, and you can compare each part of that telescope reception of the radio waves with every other one, and essentially mimic the reflection of light off the ocean, but in a very controlled way. This was joined by a very, it looks like a bunch of telegraph poles in the bottom at the same site, where you could do very long wave radio astronomy. That was known as the Shane Cross. And then there was the crisscross by another astronomer, David Christensen, which looks like a very modern radio telescope, essentially a bunch of little dishes lined up into a giant cross, again, where you can compare the information from each of those telescopes simultaneously. These were leading facilities where Australia and the UK were sort of in a battle for supremacy. And like most things, the UK probably got there first on a lot of things, but the Australians did the work better. But you get a lot of points for being there first and not getting it completely right. So Following up from this, there was also a very unique and separate effort done down in Tasmania, where Grote Reber, one of the founders of radio astronomy from the United States, received money and realized that the Tasmanian atmosphere, the ionosphere, was conducive for doing low-frequency radio astronomy. And you see here, scattered again, literally hundreds of telegraph poles across Tasmania with wires where he could go through and he could look at the sky back here in the 1950s and 60s and essentially do maps of the southern sky. He was out there doing that literally on his own. You see pictures, and he's the one who put up a lot of those poles and strung the wires single-handedly. They don't make people like him anymore. The Parkes telescope is certainly the big iconic telescope of this era, which had Australia leading the world. Taffy Bowen managed to secure investment from the Carnegie Foundation, the Rockefeller Foundation, and the Australian government to build the world's most sensitive radio telescope at the time. It was designed in 1956 and completed in 1961, and this telescope, as I said, has become an icon of Australian astronomy and physics in general. One of the things that it was involved in was making a map of radio sources around the sky, and it was able to do that with a great deal of precision, but still not a precision enough to identify what the objects were. Here is a picture of one of the sources. Now, there's a nice little arrow showing where it is, and that was done through what is pure Australian ingenuity. The radio telescopes like Parkes still gave you an uncertainty of about the size of the full moon, and that's what a sky picture looks like in that area of that size. So it's very hard to know which object is the one you're interested in. But they waited, they realized that the moon itself was going to be traveling through this part of the sky. And when the moon goes in front of the source, it turns off. And you know at that very moment that the source is on the rim of the moon. And then when the moon goes away, it turns on. And you know it's on that rim of the moon. And of course, one of those looks like a C going this way, and the other one looks like a C going that way. And the solution is you're going to get two very precise locations on the sky, which allow you to identify where this point is. That is exactly what they did, and that enabled the precise location of one of these radio sources to be found. The problem is we did not have any way to follow it further with optical telescopes at the time. The telescopes in Australia were too small, and indeed, when they looked at it, they see a jet shooting out of this object, which turned out to be about 2 billion years in the universe's past. An enormously bright object that we now realize hosts a black hole 1 billion times more massive than our sun. But at the time was just a mind-blowing discovery, which Australia missed out because it did not have the correct infrastructure in place. It did make Martin Schmidt, not related to me, a very famous person, running on the front cover of the US magazine Time. But it did spurn investment in an Australian large telescope of the optical style. And here we see Prince Charles opening up in 1974 the Anglo-Australian telescope. This is a modified copy of the US 4-meter telescopes at Kitt Peak and Saratololo. It was a 50-50 partnership between the UK and Australia, and it was built over 6 years. And I can tell you, having just spent 9 years building a much smaller telescope, that is an impressive feat. It has been the world's most productive 4-meter telescope in its lifetime and remains so today, not because Coonabarabran and Siding Springs Observatory is such a great place to build a telescope, but simply because it has been instrumented with what turns out to be the most capable instruments yet built by humanity. Of course, we did other areas. We built a reactor in the 1950s after the establishment of the Australian Atomic Energy Commission. two gentlemen went through and realized that it would be, if we're going to undertake leading edge research within the very active area of nuclear energy for a variety of reasons, everything from medical isotopes to just understanding the basic physical processes. They needed a reactor. They went through and built a copy of a reactor from England. Started in 1956. It went critical on Australia Day. Here we have Menzies going through and essentially turning it on. And this has underpinned nuclear physics in Australia for nearly 40 years. It is remarkable how much we did in that very short period of time after World War II. We also did an Australian space program. We opened up Woomera, which is the major facility during the Cold War, and actually built our own satellite in 1967, which has been the beginning of many other, mainly communications satellites since. But that satellite was a leading one at the time, and really had Australia out again near the forefront of what was going on back 40 or 50 years ago. So physics in Australia, 1975 to present, is really founded on that enthusiastic investment that the Australian government made in infrastructure in the 1950s and 70s. It set the stage for the establishment of world competitive physics departments across the country. And Australia is active in essentially all areas of physics today, with strong departments in all of the states, as well as the ACT. So what are some of the things we should think about? Well, as highlighted at the beginning, physics really is underpinned by mathematics. Mathematics is the language of physics, and we've had a lot of work done in that area, and I figured I should highlight it just briefly. We have, within our academy, Terry Tao, shown here, arguably the world's foremost pure mathematician that's alive today. His work is, I guess some of it, at least, is understandable by mere mortals, looking at how prime numbers are spaced, and he has been able to go through and essentially prove things that had evaded people for centuries. But he has really changed the style by which pure mathematics is undertaken. He's made it a collaborative venture. And those of you who hang out in your mathematics departments, Nalini, I'm sorry, collaboration amongst pure mathematicians is not always what you think of when you go into those places. And so he has the only Australian to win the Fields Medal, the premier mathematics prize for young people. But there has been huge amounts of mathematical highlights that we all use in our daily work, or not all of us, but many of us do. For example, some of the most important things that allow us to go through and understand and make progress in quantum mechanics and statistical mechanics. So the so-called star triangle relations were developed here in Australia. We've had a leading role played in development of nonlinear partial differential equation solutions. The underpinnings of the beginnings of understanding how fractals were started here in Australia. And Australia has had an incredible leading role in undertaking statistical techniques, many of which I used in my thesis and continue to use today, including bootstrap resampling, kernel density estimation, Markov chain Monte Carlo, as well as the development of smooth particle hydrodynamics, which I show you here. So what are we doing now? Well, there's many highlights. We're using physics to help develop a bionic eye. We're using photonics to go through and create orders of magnitude higher throughput communications for the future. Michelle will be talking to us next about quantum computing. We have the whole idea of physics at the boundary, where we're integrating physics into biology and chemistry. We have high energy physics, where Australia is going through and helping develop the instruments and uncover things like the Higgs boson and whatever is likely to come out from the next run of the LHC when it starts next year. We have helped establish the standard model of cosmology, where we realize that the atoms that we are made up of here in this room represent only 5% of the universe. An Australian astronomers have helped contribute to every part of this, of our understanding, helping understand the existence of dark matter, helping understand how the universe evolves over time, and my own work with the acceleration of the universe, as well as the current rate that it expands, also led here out of Australia. So what is the future of physics? Well, your guess is as good as mine. I don't like to predict the future because the whole point of doing research is that we don't know what we're doing. We have good investments in, for example, a square kilometer array. We have a synchrotron, underutilized, but certainly useful to do a whole host of things. But what I'm confident is that with continued sensible investment in people, infrastructure, and research, physics will continue to provide the basic techniques and discoveries for researchers that underpin not just our own discipline of physics, but the entirety of scientific endeavor. Thank you very much.
Thank you, Professor Schmidt, for an inspiring and wonderful overview of physics and astronomy. Do we have some questions? We have time for a couple of questions. Yes, please.
Thank you. Ross McFedrin, University of Sydney. Just to continue the story of the Braggs, one development in photonics, which you're probably aware of, and has proved valuable in industry and also applications to astronomy, is the Bragg fibre, where you take an optical fibre and you structure it to get the Bragg's law effect.
Absolutely. It's, excuse me. Bragg scattering underpins just about everything. So those photonic fibers are going to be used to do all sorts of interesting communication and manipulation within photonics. And the Kudo Center, based out of Sydney and other places, is essentially using that capability to do things. And we're using it to help subtract out nighttime skylines within astronomy. So you never know how things are going to develop, but it just shows what an amazing discovery, that his was, or theirs was.
Tony Klein, Melbourne. Just two further comments on the Bragg story. One that was triggered by Ross McFedrin's question. The quintessential Australian gemstone opal is in fact Bragg diffraction of visible light by an array of little crystal balls, little silica balls rather. The second comment is that the reactor HIFAR did not actually do terribly much for nuclear physics, but in fact neutron diffraction, which is the analog of X-ray diffraction, and same photograph of Bob Menzies at the control room of HIFAR. I have a photograph of young Tony Klein at the
Very good.
Brian, I just wanted to ask what advice you might have for young Australians wanting to undertake a career in physics or mathematics.
Well, my advice is always be, if you like it, physics provides one of the most flexible, and mathematics provides one of the most flexible career opportunities, and you can never guarantee where you're going to end up, but in the end, you almost always end up in a good place when you understand the basic way that things work, and that essential way of looking at the universe or looking at the world around us. It literally underpins almost everything, and people could go through and essentially do anything they want, from biology to sociology to finance, using those skills. And so it's arguably about as broadly applicable study you can do, and one should not be scared about future job prospects. Because trying to figure out what's going to happen in the future, having that broadest understanding is probably the best, and so the best way to future-proof yourself. So don't be scared if you like it. I wouldn't recommend doing it if you don't like it.
Thank you. Please join me in thanking Brian.